All right, so we are finishing today chapter 5, and it seems like all of a sudden like crazy, like wait, why are we all of a sudden coming up with a formula for the law of universal gravitation? Like what? And it's because it so relates and it's so interesting how it goes hand in hand with satellite motion and circular motion. So I kind of enjoy where they put it in this chapter. So we are going to get started. All right. I thought I had this all selected, but okay. All right. So what do I want to say? All right. So we are going to talk about again. So law of universal gravitation. We're going to derive that and see where it comes from. And it really started with Newton. And Newton determined that Earth had a gravitational force on the moon. Okay, so he already figured out, discovered gravity. Woo, the Fig Newton, all of it, right? Actually, so we should have named more than just the cookie after him because he's pretty awesome. So he came up with this idea of gravity, realized the moon is being pulled as well due to gravity, even though it was really far away. And he wanted to figure out, so, how much force is this? And how do we have, what determines this gravity? And so what he did is he calculated the centripetal acceleration of the moon. And we've already done that of the Earth. Remember when we did that? We can do that because we can do v squared over r, remember? Hold on, let me finish attendance. Okay, so reset myself. All right, so we remember, so AC equals V squared over R. And so if he knows about how far the moon is away from the Earth and went through the whole 2 pi r over t, knows how long it takes the moon to go around orbit the Earth and all that, he found out this number, okay? So he found out the centripetal acceleration of the moon and around the Earth. And then he wanted to compare that. Well, that's an acceleration, and we know objects on Earth accelerate at this. So he did a comparison. So he took that tiny number. And again, why is it so tiny? Well, because it takes almost a month for the moon to go once around to only do one circle. So its acceleration is quite low, even though it's traveling quite fast. All right, just like the Earth around the sun, which takes an entire year to go one circle. So anyhow, he took these numbers and divided, and he noticed, it's 1 over 3,600. Well, then he thought a little bit more, and it turns out the moon is 60 times farther from Earth's center as objects on the surface. So if we draw the Earth and you had some object here, the moon is such where this distance is compared to the center of the Earth. So this thing compared to this thing is 60 times further. This is 60 times Earth's radius, basically, okay? And he goes, oh, well, I know how to get from 60 to 3,600, and hopefully you guys know how to get without a calculator, and you realize it's the square. He goes, oh, if I square 60, I get 3,600. So maybe it changes and it's proportionate as a square function. And not only a square function, do you see it's 1/3600ths. So it's 1 over the square. So he said force of gravity must be, hopefully you know that's the proportional symbol. That means proportional to. So force of gravity is proportional to 1 over r squared. So where r is the radial distance, especially if something goes in a circle, r is radius. So we many times keep using the word radius as a distance. And so he made a connection there. Now, besides how far away, he also realized that force of gravity must be dependent on an object's mass, okay? And so, the bigger the Earth is massive-wise, the more massive the Earth, then it can pull on objects more. But since we also know Newton's third law of when one thing pulls on another, the first thing, the one object pulls on a second object pulls on a first object, right? Newton's third law, then it isn't just dependent on Earth's mass. It must be dependent on whatever other object's mass too. So if you have a force of gravity on an object, it depends on both masses, not just one mass. Okay, we're kind of used to so far dealing with just one mass. If I want to know the weight of this object, right, then all I need to know is its mass and gravity. Okay, well, we didn't know. So, but the pull, how much to pull depends on not only the mass of this object, but the mass of the Earth that's underneath it. Okay, it's kind of like, I always compare this to magnets. If you have a magnet, okay, that doesn't do anything. We need two magnets, right? Or you need a magnet and another object, and it's an interaction between those two. It isn't, you can't just have one. And if you make one magnet, stronger, that's one thing. But if you make them both stronger, right, then there's obviously even more force between it. And so that's the same thing. If you have two objects that are really massive, there's going to be a lot of force of gravity between them. Okay, it's not just one. Okay, so we're going to expand from this to including masses in it. And so force of gravity is proportional not only to over r squared, we're going to make this our fraction line here, but in the numerator should belong the mass of one object, which could be the Earth, and the mass of the other object, which could be the object that you think is, let's say, falling towards the Earth or sitting on the Earth. So it's always dependent on two objects. And it doesn't just have to be the Earth or something really big. This is what the law of gravitation states. Here it is. Okay, way too wordy. All right, every particle in the universe attracts every other particle with a force that is proportional to the product of their masses. Didn't we just see that? M1 times M2. And inversely proportional to the square of the distance between them. In other words, divided by r squared. Okay? But what's so important is it's every particle in the universe. Okay? This force acts along the line joining the two particles. What does that mean? It's linear. It's between them. So here's a wonderful picture. It's very simple. Here's one object. Here's another object. They are in love, mutual love. All right. So we know that M1 here is pulling on M2 with this force, and M2 is pulling on M1 with this force. And what about those forces? They are the same. They love each other equally. All right? The force is the same. Okay? Newton's third law. If this is pulling on this one, this is pulling equally on this one. Okay? And it's a line of force. So it's that force exerts like it's a rope between them. Okay? Imagine it's like tug of war. All right? They're pulling mutually. One pulls harder, the other has to pull harder too. Okay? So F1 equals F2, and here's our magical formula. I had the little proportional symbol up above, and all I've done now to make an equal sign in the formula, all I've done is put a constant. And we call this constant big G. All right, you like that? Why do we call it big G? Because we already got a little g. Little g is the acceleration due to gravity, right? And on Earth, it's 9.8. On the moon, it's whatever, 1.6, whatever. We don't care. But big G is a constant. And we call it the universal gravitational constant. All right, again, better known as big G, if you want to communicate with me. Wait, if you ask me a number, you go, what's G again? You go, what's big G? And then I will give you the number. Of course, this number I will give you on a formula sheet. We don't like memorizing anything because your teacher can't memorize anything, all right, which means you don't have to. All right, and that number is 6.67 times 10 to the minus 11. Now, what do you notice about big G? What do you notice about big G? I hope you notice big G ain't big. The symbol is big, okay? It's a capital G, but this is little, tiny. All right? Really, really small. That is the best news you've heard today. You know why? You know why? I'm gonna pick on Q because I know Q. Because if that number was big, every time his little annoying brother comes over to him, he would be gravitationally super attracted to him, and he'd be stuck on him. He already thinks his little brother's stuck on him too much. They would like suck together like giant super magnets, and he wouldn't be able to rip them apart from him. That would be horrible. Okay, so the good news is that big G is a little number, because if every particle in the universe attracts each other, my goodness, we want that attraction to be pretty darn low. Because otherwise you'd be walking around, suck. Oh, I'm too close to my computer. Oh, I got too close to my brother. Whatever. Okay? All right. We don't want the pen in your hand to like fly to your face. So that would be horrible. So because big G is such a small number, for it to be substantial, these masses in here, or at least one of the masses, needs to be planetary big before you're going to really feel anything. Okay? So you need these to be substantial. Okay? If not planetary big, how about think mountain big? You need a lot of mass before it's measurable. Okay? Mountains are measurable. A mountain, okay, of dirt has enough gravitational force to change some things. Okay? And that's where there's a difference of this concept you'll learn later about, called center of mass versus center of gravity. Where the center of mass isn't always where center of gravity is of something, because of this concept of things having their own gravitational field. Okay, so why are we doing this chapter? Well, we're soon to reveal that. Okay, all right. Now, we already know that we've already had a formula for force of gravity, right? We said, well, Ms. Jones, you told me weight is the force of gravity and it equals mg. And I'm like, yeah. So again, if I have this in my hand, I can calculate the force of the Earth on this object by taking the mass of this object times the gravity, which we know on Earth is 9.8. But that's been, you remember already, that's experimentally calculated, right? And so, okay, we can do it. But now we're going to expand this by setting these things equal to each other. So now I'm like, hey, this is force of gravity, and this is the formula for force of gravity. So we're going to make them equal to each other. So we have mg equals big G mm over r squared. Now it's kind of a mess, because we got a lot of m's. We wish we actually had M&Ms, didn't we? You could eat those right now. All right. So I say here, label whose m's and r's are. What are we going to do here? Who's what? So imagine, okay, we have the Earth, and here, I'm going to make this U. There, this is U. All right, and here's the Earth. Okay, so in this formula, whose mass is this? Is this the Earth's mass? Well, if you weighed, this would, we're talking about the weight of U. And the weight of U, that would be the mass of U. Okay, so this would be U, or whatever object is sitting on the Earth. Okay, whatever. Okay. What about these? What did we say here? Remember, there's two things, and it would be between U and the Earth. So one of these, to solve for the force of gravity, is U, and the other one is the Earth. Okay. And then this always has to be the distance between the objects, that would be U and Earth in this case, objects. I'm going to add, this is super important because this is where people screw up, distance between objects from center to center. Now, why am I saying center to center? Because if I didn't say center to center, what would you, if you were standing on the Earth, what would you tell me the distance is? You'd say, well, you're touching.
0.
The answer's 0. Well, that wouldn't work out very well. What if I plugged in 0 here? People go, well, you can't answer it mathematically. Yeah, you can. If this was 0 down here, if you divide by 0, you'd get an infinitely large number. Do you realize that? If this number was close to 0, okay, approaching 0, this would approach infinity. The force of gravity between you and the Earth is not approaching infinity. So you have to remember you have to measure from center to center of objects. Now, in this case, what would you make r in this problem? In this case, you would make the distance the radius of the Earth. Now, you could try to add half your height to the radius of the Earth, and how would that work out with sig figs? You wouldn't even show up. So basically, right, you would just use the Earth's radius to go down here in that case. Okay? Now, what do you notice can happen here? What can we do? You are here on both sides of the equation. So we're going to go bam, bam. That's like our favorite thing in physics. That happens so often, right? And now we have a new formula to solve for little g, all right? That's gone. We can say g, little g is big G m over r squared, okay? And this becomes, look, it's another box formula. Must be important. Okay, now please don't confuse force of gravity and gravity. At some point, and on one question, I may ask, what's the force of gravity between whatever two objects? And I would ask for F sub G. This is just G. Do you notice what happens if I have a force and I get rid of, from that calculation, the mass? We know F equals ma. If I get rid of m, what do I have? I have a. Isn't gravity an acceleration? So please realize, I don't know why I can't write today. Acceleration. All right, so this is the acceleration due to gravity, okay? Please don't think this is a force anymore, all right? This has the units like all accelerations, meters per second squared. All right, so this is, as it says, solve for the acceleration of gravity at the Earth's surface. And I bet you won't believe it, but if you plug in the value for the universal gravitational constant, here the mass of the Earth, here the radius of the Earth, guess what you'll get for G? You'll get 9.8. Isn't that amazing? Okay. Is that true everywhere on Earth? Well, kind of. All right. The deal is everywhere on Earth the same R? Well, you're going to do one, either I think it's on today's worksheet or it's on Monday's worksheet, where you're actually going to calculate G and see if it differs much if you are on the top of Mount Everest. Theoretically, it should. What should happen if you are on, aren't you further away? If you were standing here, aren't you further away from the center of the Earth? Isn't the force, just like magnets being separated more, shouldn't the force be less? And the answer is the force is less, and so then the acceleration should be slightly less too. So the acceleration due to gravity would be less on the top of Mount Everest because R is greater. Or if you were to dig a giant hole into the Earth, right, it should be greater. Now, I don't know if you realize this, but if you've ever seen those globes that have the bumps on them to represent the, the relief, the mountains and everything, those are not to scale at all. If you really wanted to compare what this is not true. And if they made a true model of the Earth where there were the correct bumps, you wouldn't be able to feel the mountains. The mountains are really so small, so it isn't a big difference. Okay, there is some, theoretically speaking. Okay. All right, so until G was measured, the mass of the Earth wasn't known. So this is, I love this stuff because it's empowerment. I've just made you smart in so many like NASA type and, astrophysics ways because you can find out anything about all kinds of things as long as you know. If you can watch, if you are an astronomer and watch something travel around another object, you can figure out the mass of the object that it's going around. Isn't that amazing? Okay, it's pretty cool stuff. All right, okay, so in fact, that's where we're going to go here. Let's talk about satellites. All right, this is one of my favorite pictures too. All right, so I'm going to draw the Earth and imagine, obviously not to scale. All right, you are going to stand here. And you are going to shoot a gun. All right. How timely our today's environment. Okay, so, all right. So here we go. Someone wants to shoot a gun. Now, if they shoot a gun, we know what happens to that bullet because we did projectiles. And when we do projectiles, doesn't it go like this? And it goes, right? There's projectile motion, right? Our parabolic path, blah, 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 whatever. Okay. All right. What if he shoots a gun and he shoots it? It's faster. It's a higher speed. Right? Yeah? All right. This must be a really fast gun. Okay. So it is falling, right, all the time. But what if it is really fast? You figure out what's going to happen. This is what happens when people have guns. All right. Did you like that? All right. So what happened? What happened was his bullet was able to orbit the Earth. This is true if, do you realize it's falling? Do you realize that this bullet, in a sense, is taking a circular path because of the force of gravity on that bullet? Isn't that an inward force? Isn't the circular motion? Don't we need an inward force to make something go in a circle? What if you pull on it too much? It's going to make a tighter circle, and in this case, it dive bombed into the Earth. If you have a velocity such where the velocity is such that the force of gravity is just the right amount to make it go in this circle, then you can orbit another object. So it can be Mr. Sun and the Earth going around, right? And where that force of gravity and its distance from the sun, which determines the force of gravity, is just right for its speed, and it's in a stable orbit going around, okay? So a satellite is falling or accelerating always, if it's around the Earth, towards the Earth, but its high tangential speed keeps it from hitting the Earth, all right? So it's being forced into a circle because of gravity, but yet it never ends up, right? It's not too tight of a circle, so it ends up in the stable orbit. Okay, so what are we going to do? We're going to do our favorite thing again. We're going to set two equations equal to each other. Sorry, I lost my little line here. So force of gravity, we just learned, was big G mm over r squared. And that we're going to set equal to what? Well, what do we want it to do? We want it to go in a circle, so we want to set it equal to centripetal force, Fc. And I'm just going to squeeze this in. So Fg equals Fc. So I'm going to take my Fg formula and set it equal to our last set of notes, our what we've been working on with mv squared over r. Now we have to be careful again. We want to label what these things are. All right, that's again important. So this first object, let's call this the central object. And normally then it would be the central planet, okay? It doesn't have to be a planet, but there you go. It could be the sun, right? So really, I guess I should have just said central object. And then this is what's going around the other object. And we normally call that then a satellite, right? Okay, so we have our central object and some kind of satellite, okay? And what about this M? Which M is this? We had trouble with this with our lab, all right? What mass do we plug in here? If we're solving for how much centripetal force is necessary, didn't we say this is the mass that's going in a circle, right? Mass, right, going in circle. Which mass is that going? What mass?
Satellite?
Yes, so this is the satellite. Okay, which is really important to know what's what. So we can once again, right, what are we going to do? Our favorite thing, cancel out masses. So the mass that goes away is the satellite mass, okay? Now, this R is the same R. This R is the radius of the circular path, and this is the distance between objects. And that is going to be pretty much the same thing, Okay, so we can take one of these r's and go bye-bye, right? Okay, now that's a mess, right? So what do we have left? We have big G, M, and that's it. No, sorry, an R, one R. I lost the R. Big G, M, R equals V squared. Well, we don't like that formula normally, so what do? We square root both sides, so we just have V, because many times we're interested in V, okay? So we say now V equals the square root of big G M over R. Now, what did I labeled this ME, and I should have done that here too. Traditionally, you'll see an E here, and that's because this would be Earth's mass. Now, it doesn't have to be Earth's mass. It has to be whatever the central object is. I almost feel like I want to label it, MC. But how about I just label central object? And a lot of problems we do, it would be Earth. But it does not have to be. It could be Jupiter. You could be trying to... Okay. Here's awesome. So you're working for NASA, and you are asked, you guys want to put a satellite around Jupiter, and you want to, watch what it's doing. What do you need? What are you going to do? Two things. One is if you want to know how far, if given how far out from the planet, let's say you're taking pictures of it, you want it to be a certain distance away, you would put that information, and you would know what kind of speed you need to launch that or have that satellite going so it would stay in a stable orbit above Jupiter. All right. Or if you know what speed you want to set it off, you could figure out what distance you need to place that satellite from the center. Now remember, this is measured from the center, and I'm going to label this again. This is always orbital radius. Everything, an orbital radius is measured from center. We don't have to, I wanted to say from center to center, but for the satellite, okay, here you got some planet, and here you have a satellite that you've launched out in space. Now, I always say, make sure you include this radius of whatever planet it is, because if you only are given how far it is from the surface of the planet, and this is not crazy amount bigger than this, then your number is going to be all screwed up. So this R is always going to be this. Now, some people say, well, what about the satellite? Don't you have to measure from the center of the satellite? Again, the satellite, I assume, is not very big compared to the radius of whatever planet you're going around, or moon or sun, that it's not going to influence it. But this Earth or whatever planet radius will. So be very careful when you do problems. I'm going to say it. I'm going to say it again. And I'll say it another time. And this is where people screw up this chapter. They go R, and they just grab any old R. M, they just grab any old M. You got to put the right M. Like, you can't put the satellite's mass in here. This problem's going to be wrong. You're not going to put the satellite's radius in here. You're not going to put the Earth's radius in here. You need the orbital radius to be plugged in here. Okay? So, great formula. All right? So, this is normally considered, a satellite. So, this is the velocity of the satellite. And a satellite is just an object that orbits another object. Okay? Our moon is a satellite of the Earth. I don't know if you've ever heard that used that way, but absolutely. Okay? And other things that are cool. Again, if we know the velocity of some satellite, and you know how far it is away, and you know the gravitational constant, you can find the mass of any planetary object. Okay? It's pretty cool. Okay. There we are. So we are armed with three formulas: force of gravity formula, gravitational formula and satellite velocity formula. And this really is one of these things that gives a lot of predictive tools to stuff that you can work on. All right, so you have a worksheet today to work out the rest of this hour. But before you do that, I want to talk about a few things. One is, when is our test over this? Someone already emailed me like, hey, you laid out the next 2 weeks, but like, when are we doing this test? I have no option. It's going to be during exam week, so the Monday, for you guys, it would be the Monday of exam week, the 18th. So next Friday, we're going to have a review over this chapter. I would have liked to have an extra class period, but the problem, and I would have loved to give a test on our Thursday or Friday or the last days of our semester. I cannot do that. First of all, we only have a 1 hour, it's a half day. We only have a 1 hour period and we have no asynchronous time. We have 10 minutes of asynchronous time. So I can't fit it in there. And I have a thing from administration that laid out what's allowed. And it says, we can't do anything. We're not allowed to give a test during the normal official exam time. Whatever. Okay. So it ends up, so our test over this chapter is going to be the 18th, okay? That's all I know. Our exam window is from the 18th to the 22nd. So remember I said we're going to have an asynchronous, can't call it exam, how about a cumulative assessment? Remember, one that can't hurt your grade, and that you can only, if you do better on this cumulative assessment, which I have not created yet, then I will replace one of your test scores. I have to figure out how I can manage to do this in Canvas. I'm working on it. But I may go in and just change your worst test and just bump up to reflect the percent you got on this cumulative assessment. This cumulative assessment is going to have a window and it's going to be asynchronous. So I think I'm making the exam window. I think I just started creating it. I can't remember because I got 2 classes. But it's going to be a window from that last week in exam week, 18th to the 22nd, whenever you want to do it. You can also choose not to do it. It can't hurt your grade. I wouldn't think that's a very smart thing because this is a good thing for you to really get an idea on your progress in this class. And also, like, should I take the AP exam at the end of the year? How am I doing? How am I going to do in college? Where we do have cumulative tests, all that kind of stuff. Okay? All right. So we have a test over this test is for Chapter 5. That's going to be our last test for the semester. And then you potentially could substitute. You could take that test and the next day or the same day take our cumulative assessment and maybe substitute it if this was your bad one. Although I think this test could be really good. For people who are really good at dotting their I's and crossing their T's, this is a good test. For people that tend to make a lot of mistakes on tests, this one is a mathematical nightmare. And let me tell you why. Because people do this. They forget to change kilometers, which most astronomical distance are given in kilometers, and they forget to change it to meters. There's mistake number 1. People see some formulas have r squared in them, but yet others don't. So our acceleration is v squared over r, it's just plain r, but in this formula, r squared. And all of a sudden here, this formula has just an r and not r squared, but there's a square root. People forget square roots and squares. People forget that we need kilograms. People forget we need kilometers. And it's a mess. It shouldn't be, but there's just too many little things for people to watch. Overall, people know what they're doing, and then they screw it up. And then people plug in the wrong radius. Like I said, they forget to include the radius of the Earth, all these wonderful things. Oh, by the way, those numbers for the radius of the Earth